Okay, let's demonstrate that the following is a polynomial function and infer its behavior. Then we want to determine the leading term. So we know that polynomial functions have a constant finite difference. Right, so let's start by determining the finite differences. And let's start with the first finite differences in red. Right, so you can notice that the change in, we know that finite differences is basically delta y over delta x, and we can notice that delta x here is always 1, so we just have to divide everything by 1. So we're just really looking at delta y, right? So this is positive 1, this is positive 1, right? 2 minus 1 is 1, 3 minus 2 is 1, 4 minus 3 is 1, and so forth. Okay, so let's look at our first finite difference. I'm going to do that in red. 4 minus 9 is negative 5, 1 minus 4 is negative 3, 0 minus 1 is negative 1, 1 minus 0 is 1, sorry, 4 minus 1 is 3, and 9 minus 4 is 5. Okay, so that's our first finite difference. You can see that the first finite differences, or the first differences, are not constant. Let's take a look at our second finite differences. So our second finite difference is negative 3 minus 5, right? So in this case, it's going to give us 2, negative 1 minus negative 3, which is 2, 1 minus negative 1, which is 2, 3 minus 1 is 2, and so forth. So you can notice that our second finite differences are constant, and because our finite differences are constant, this is a polynomial function. Because the second finite differences are constant, we can understand that the polynomial function will have a degree of 2. Okay, so therefore it's a quadratic function. So because it's a quadratic function, right, y should be equal to ax squared plus bx plus c. Okay, now we want to determine the leading term, right? So the leading term here is ax squared. The last thing we need to do here is we need to find the leading coefficient. Let's solve for a. This is your leading coefficient, right? And a times n factorial is equal to the finite differences. We can use this equation. A is equal to the finite differences over n factorial, and the finite differences here are basically equal to 2. I'm going to divide this by the degree factorial, which is 2 factorial, which is 2 over 2 times 1, which is 1, right? So in this case, a is equal to 1, so our leading term here is x squared, right? So that's our leading term, and we've proven that it's a polynomial function because our second